Hello everyone. In this session, we're going to learn about the bitwise operators. The bitwise operators allow you to manipulate individual bits of a number. These are the most widely used operators with respect to embedded systems because we have to work around on individual bits. Now, using the bitwise operators, we can verify a particular bit is 0 or 1. If you want, you can change it, like we can set a bit, or we can clear a bit, or we can toggle a bit. All these, if you want to work on individual bits or a group of bits, then we have to play around with bitwise operators. Along with this, we also have shift operators which will help us to shift some bits towards the left or towards the right. One key point is the bitwise operators can only be applied for integral types. When I say integral type, it means we can apply this on characters. You should treat characters as 1 byte integer, short, int, as well as long. It can be applied with signed as well as unsigned. Commonly it is applied on unsigned, right? So let us try to see what are the bitwise operators provided by the C language. The C language provides 6 bitwise operators: bitwise AND, bitwise OR, exclusive OR, left shift, right shift, and the complement, right? So you can just see the symbols out here. Okay, this same symbol you can observe we had already used this as address of operator, right? Now, depending upon how you use it, the compiler will understand is it an address of operator or a bitwise AND operator, right? And then please be careful, because in mathematics this symbol we might end up using it as a power symbol, but in C there is nothing called as power symbol. Instead it is exclusive OR, right? This is your left shift, right shift, and this is your complement. The first 5 operators are binary operators. The complement operator is a unary operator. Now let us try to look into individual operators. Okay, what are the operations they do, and then how do we apply this? Let's take up the bitwise AND operator. The bitwise AND operator compares each bit of its first operand to the corresponding bits of its second operand. And observe, if both bits are 1, the corresponding resulting bit will be 1. Otherwise, the bit will be 0. Let's take an example and try to understand. Okay, I've taken an example wherein one of the variable has a value 4, another variable has a value 2, and the binary representation is mentioned here. Remember, whenever you talk about bitwise operators, you should first write down the binary equivalent of the number, and then you have to work on the individual bits, right? Okay, you should not treat the same as logical operators, because logical operators, it's like you take the entire number and try to observe that is it 0 or non-zero. Whereas in the bitwise operators, we have to first write down binary equivalent and then perform the operation on individual bits, right? Now let us see, okay, what it does. Now here we have 0 and 0 here, right? What will the resulting bit? It will be 0. Here again it will be 0. Here it will be 0, right? Here also it will be 0, 0. What is 1, 0? It is 0. 0, 1, again 0. 0, 0 is also 0. What will be the final result? All the bits will be 0. All the bits are 0. Even decimal also the value will be 0. Let us take up another example. We have 6 and 3, right? Now again, if you look into this first bit, it is 0 and 0, it will be 0. Here also 0, 0, 0, 0, 0, right? Now what is 1, 0? 0. What is 1, 1? It is 1. 0, 1, it is 0. Only this it will be 1, everything else will be 0, right? So if you convert this into decimal, what is the value? It is 2, right? 6 and with 3 it is 2, right? Okay, remember, logical operators will either give me 0 or 1, but bitwise operators does not give me only the final. I'm talking about the final answer. It will not be only 0 or 1. You have to perform in individual bits and then okay, based on that, the final answer, if you take it back in decimal, then it could be different values, right? I hope this is clear with respect to AND operator. Fine. Now let's move into the OR operator, right? Again, here it compares each bit of its first operand to the corresponding bit of its second operand, and you can observe, if either bit is 1, meaning if either the bit is 1 in the first operand or the second operand, the resultant bit is 1. Otherwise, the result the corresponding result bit is 0. When it is 0? When both are 0, right? If both are 1, it is 1. If either one of it is 1, it is 1, right? So let us try to look into this. 0 0, what is 0 0? It will be 0. This will also be 0 0 0 0. What about this? Either one of it is 1. Yes, this will be 1. Here it will be 1, right? And then this will be 0. Okay, clear? Now if you convert to decimal, it is 6. Clear? Okay, let's take one more example to understand OR. Fine, I have written two values, 5 and 3. Why don't you guys quickly pause this video, write it down, and then let us try to see the result. Done? Okay, so what is the result here? It is 1 here, it is 1 here. What is 1 and 1? Remember, both the bits are 1, so the resultant bit will be 1 or 0. When you perform binary addition, 1 and 1 will be 0 with a carry 1. But when you perform the ORing, 1 and 1 is 1. Okay, this is the difference here when you compare it with addition of two bits. ORing, 1 OR with 1 is 1. It is not 0, right? Okay, clear? So what is in decimal? It is 7. Clear? Right. Now let's look into the XOR. In XOR, if both the bits have the same values, like if they have 0 and 0, or if they have 1 and 1, then the resultant bit will be 0, right? If one bit is 0 and the other bit is 1, only then the corresponding bit will be 1. Remember, if one bit is 0, the other one is 1, only then you can just observe this point. One bit is 0, other bit is 1, only then it is 1. Clear? Let's take an example. Right, now here it's a very simple example, right? What is 1 0 here? It is 1, and 0 1 is 1. If both are 0, it is 0. If okay, and in this example we don't have both 1s, the final result will be 6 here. Now let's take up this again. 1 0 is 1, 0 1 is 1. Please remember here, this 1 OR with 1 will be 1, but 1 XOR with 1 will be 0, right? 1 XOR with 1 will be 0, wherein if you use a OR, your bitwise OR with the pipeline character, that will be 1 there. So here we should be more careful. Fine guys? Okay, so we have learned about the AND, OR, as well as XOR. Fine. Okay, now let's look into the complement. I said complement is a unary operator. It works on only one operand and it flips every bit. If a bit is 0, it's going to convert to 1. If the bit is 1, it's going to convert to 0. So if I take this input, right, so you can just see only one bit is 1, every other bit is 0 here. Okay, now what is the complement? Every 0 bit will be converted to 1 and every 1 bit will be converted to 0. Got it? Okay, do not confuse with your logical NOT operator. The logical NOT operator is represented with the help of this, right? Okay, this is logical NOT. Okay, wherein it converts true to false, false to 0. Whereas bitwise NOT, it is complement. It's also called as bitwise NOT. Okay, remember, in case if you had 4, if you perform logical NOT, it will become 0. But here this value is not 0, right? What is the value of this? Yes, if you take it in hexadecimal, right? If you take it in hexadecimal, right, you can just take this 4 bits. What is the value? F. And here it is 8 plus 2, which is A plus 1 is B. Clear? Okay. It is FB. It is easy to convert from binary to hexadecimal, right? If you convert the same value to decimal, remember, in that case you will see a small difference here. Remember, the MSB bit is generally called a sign bit. Here the sign bit was 0 for positive, and since the sign bit is 1 here, it will be negative, right? But the value, if you want to get the value, again you need to perform the 2's complement of this, right? In decimal, if you want to get it, you need to perform the 2's complement. I hope you guys have studied this in digital electronics. So we have to apply 2's complement of this. Okay, so if you apply 2's complement of this, you basically get -5. Clear? Okay, fine. Now let's move into the shift operator. You have two shift operators, left shift and the right shift. The left shift adds some 0 bits from the LSB side. Like if I write an expression like x left shift by y, it will add y number of 0 bits from the LSB side. When I say LSB, that is from the right hand side. Okay, on this x, the MSB bit will be out. The MSB bits, right? Y number of bits from the MS will be out, and then from the LSB side, y number of zeros will be added. Take a simple example. We have this. Assume that x value is 4, y value is 2. Now if you take up this one, you know what happens? 2 zeros gets added up here. When you add up 2 zeros here, then these 2 bits will be out, right? Okay, so this will be your number, right? These bits get shifted, right? Clear? This will be the value. How do we get this? You can just observe this value was shifted here, right? This was shifted to this place, this was shifted to this place, and you can observe this 1 is shifted to this place, then 0 is shifted here, right? This one, and these are the 2 bits which were added, which is 0 bits. Clear? Right. We also use left shift operators if you want to multiply a number by 2 power n. Like if you want to multiply by 1, 2, 4, 8, 16, right? In that case, you can use the left shift operator, right? Okay, fine. Left shifting by 1 is same as multiplying by 2 power 1. What is 2 power 1? Is 2. Left shifting by 2 is same as multiplying by 4. Is it 4? 2 power 2? Yes. But left shifting by 3 is multiplying by 6 or 8. It is 8. 2 power 3 is 8. Right? So again, even in this example, if you observe, my initial value was 4. This was 4. And you know what is this value? It is 4 into 2 power 2. 2 power 2 is 4. 4 into 4 is 16. Clear? Now let's look into the right shift operator. What does right shift do? It shifts the bits towards the right hand side. Clear? Okay. While shifting, it will remove y number of bits from the LSB side. It removes, right? Like for example, again, if I take the same example 4 and 2, if I want to shift by 2 bits, you know what happens? These 2 bits will be removed, right? This bit will be removed, this bit will be removed, and these bits get shifted, right? Okay, but what gets added here? Is it always 0, right? So there is little bit to study about this. In case if the MSB bit is 0, right, then 0 gets added here, right? But in case if this MSB bit is 1, then 1 gets added here or 0 gets added here. That depends upon x is signed or unsigned. If x is unsigned, even if it is 1, what gets added is 0 and 0. If it is unsigned, right? If it is signed, what gets added up? Okay, 1 gets added up. If the MSB bit, or you also can say that it is a signed bit, is 1, right? I hope, okay, the basic things about all the 6 operators are clear. So we are going to demonstrate the same thing through the program. Okay, now let's try to understand how the bitwise operators work through the programs, right? Now I have read 2 numbers and I'll be calculating the result depending upon various bitwise calculations, and then I'll be printing the result here. Now to begin with, let us try to talk about AND operator, right? So we have seen that AND, the final bit will be 1 only when both the bits are ones, and then if either one of the bit is 0, the final bit will be 0, right? So we've written the code. Okay, now let us try to compile this program. Okay, before we compile, let's save this, then compile this program, and then let us try to execute this. We need to enter 2 numbers. Whichever numbers you're trying to enter, make sure that you write down the binary equivalent of this. Like for example, let us say I'm taking a 4 and 2, right? See, computer will give you the result, but first thing what you should understand is, have we understood correctly or not? So first write down the binary equivalent of 4. It is 1 0 0. 2 is 0 1 0, right? So what will be the result of ANDing here? It is 0 0 and 0, and again decimal value, it is 0 only. Let's verify. Fine. So this is working fine. Now let's take up some other input. Now let us say 5 and 3, right? Okay, fine. We could see the output there, but still we will try to understand. This is my 5 and this is 3, and here, right, now 1 0 was 0, 0 1 was 0, 1 1 was 1. Clear? Fine. Now let us again take up some other input. Now let us say we say 6 and let us say we say 2, right? Let us take 6 and 2. Write down the binary equivalent of this. 6 is 1 1 0, that is 4 plus 2 is 6, 2 is 0 1 0. Now what is the result for this? It is 0 1 0. Clear? Okay, now we got the result here. Fine. Now let us take up the OR. Okay, let's save this. Let us try to work with the same inputs, but remember, when you do any changes in the source code, you have to recompile your program, right? We'll try to execute this. We'll take a 4 and 2 itself, because we already written the binary equivalent of 4 and 2. We just need to perform the ORing now. So what is 1 OR with 0? It is 1, and this is also 1. So in decimal, what is the value? 4 plus 2 is 6, right? Okay, got it. Now let's try to again run and then try to give 5 and 3. If you have 5 and 3, okay, so this will be 1 1, this will also be 1 only, right? So what is the value in decimal? It is 7. Fine. Now let's again take up this 6 and 2. What is the result? If you perform the ORing here, it is 1 1 0. What is 1 1 0? It is 6. Clear? Okay, fine. Now let's try to verify with XOR. In XOR, remember, here 1 0 is 1, 0 1 is 1, and then 0 0 is 0. This will remain the same. Here again, remember 1 1, but this is very important here. This will turn out to be 0, right? And here this will again turn out to be 0. Let's quickly verify this. Compile it. Execute this. What is the first one? 4 and 2. The result is 6. Then second one, it is 5 and 3. The result is 6. Then again, okay, let us say it is 6 and 2. What is the result? It is 4. Okay, so I hope this is clear, right? Now let's learn about the shift operators. Now what we learned with the shift operators, you have the number and then this number of bits will be added from the LSB side for the left shift. This left shift, remember left shift in the sense, okay, we'll be adding the bits from the LSB, right? And we also learned that left shifting is same as multiplying by 2 power n, right? If I take up a number, let's say 5, then if I say 2, what is 2 power 2? It is 4. What is 5 into 4? It is 20, right? If you want to understand through binary, so what is 5? 101. This is my 5. Okay, so if you want to add up two zeros, 10100. What is this? It is 20. Got it? Okay, so you can take up any other numbers also and you can understand. Let us say, I'll say 3 and then let us 4. What is 2 power 4? It is 16. 16 into 3, 48. Clear? But always write in binary so that you can easily understand. This is 3 and then how many zeros you need to add, right? So 4 zeros, 1 2 4 8. This is 16 and this is 32. 16 plus 32 is 48. I hope it is clear. Right, now we'll also try to understand the right shift operator. Fine, again we need to recompile it, execute it again. Let us say 4. Remember 4 is this 100. Okay, now how many bits you want to remove? Let us say you want to remove 2 bits. So if you want to remove 2 bits, right, so these 2 bits will be out. If 2 bits are out, what is the remaining value? It is 1. Clear? Okay, now let us take up something like 15 and again let us take up 2. Now what is 15? 1 1 1 1. Again if you take out these 2 bits, what is the value? It will be 3. Clear? Okay, now what is 15 divided by 2 square? 2 square is 4. What is 15 by 4? Integer division. It is 3. See, for floating point division is 3.75. If you perform integer division, it is 3 only. Got it? I hope it is clear. Left shift and the right shift operation. Now let us try to understand the negation. Right? We need to treat only one number because the unary operator. Right? Okay. Now let's try to compile this again and try to execute. And I said that any positive value will turn out to be negative, any negative value will turn out to be positive, right? 4 will turn out to be -5 or any negative value will turn out to be positive. Or the better way to understand is you can print in hexadecimal, right? So we can just print in hexadecimal so we can understand it better. Fine. So if you want, you can also read the number in hexadecimal, or if you want to read in decimal itself, fine, that's not a problem. But try to print this value in hexadecimal before performing the complement and try to do the same thing after performing the complement, right? Okay, so let's try to compile this, run. Now let us say it is 5. So what is the binary equivalent of 5? It is 05. And then can you just observe it is FA. Why is there so many F's here? Because it is a 32-bit number. Remember, it's a 32-bit number. Clear? Okay. Now when I take up something like -5, this is my value, right? And this is, okay, the reverse of this, right? Before this, everything else turns out to be 0. Clear? Okay, fine. Okay. Yes, we will be working on many other programs on Bitwise operators. We will show you how to clear a bit, how to verify a bit, and print a given number in binary format, right? All those things, but that, okay, will be done after we learn about the if-else statements and the looping constructs, right? For the time being, we're going to stop here. Thank you.